Guns N' Roses used to say, "Welcome to the jungle." Welcome to the type system. I'm Daniel, and in this video we're going to discuss some seemingly small problems related to inheritance. Because we are in a new chapter, it makes sense for us to start a new package. So go ahead to Lectures and create a new package. Let's call this Part 5 Type System. And in this Part 5 Type System package, let's create a new rocking inheritance Scala object which extends app. Now, there are a number of things that I want to talk about, and in this lesson I'll assume that you already know how to do inheritance with classes and trait, including trait mixins. Alright? First of all is a small convenience, just to warm you up. Let's say I'm writing an API for an I/O library, so writing and reading things. So let's say I have a small trait, let's say writer, which writes things of type T, and it has a def write method which writes a value of type T, and this just returns a unit. I don't really care. Okay, let's also have a trait. I'm going to name this closable for closable resources. This has a method called, let's say, close with some kind of status or something like that. Okay, this also returns a unit. I don't really care. Okay, so we have a very small API. And we also have a trait. Let's call this generic string of values, right, that we read from our resources. And we have some methods here. For example, the for each method. So for each value that we read from our resource, we apply some kind of function. So f from t to unit. And this guy returns unit. Okay, so we have a minimal API for our little imaginary library. Now, the convenience here is that if we have a generic stream that also mixes in some other traits, we can define a method called, let's say, process stream, annotated with a type parameter. And if we have an idea about the type that we want to receive, like a generic stream that mixes in some closable and writer, but we don't know who exactly does that, we can simply say generic stream of type T with writer T with closable. So this guy right over here, generic stream with writer with closable, is its own type. And it has access to all our API. So for example, we can say stream.forEach do something. Let's say print line and stream.close with some kind of status like 1 or 0. So this is our little convenience. Whenever we don't know who exactly mixes in our specific traits, we can use them all in a specific type as a parameter to a method. Okay, this is item number 1 as a warm-up. Item number 2, related to inheritance, is, I think you saw this coming, the diamond problem. And because I started with welcome to the jungle, let's define a small jungle hierarchy, like trait animal, and trait lion extends animal, and trait tiger extends animal. And let's say the animal has a small method called, say, name, which returns a string. So if I say trait mutant extends lion with tiger, this is perfectly compilable code. This inherits the defName method from both lion and tiger, but because the defName method is unimplemented, the compiler doesn't really care. If the mutant is a class, then it's just forced to override the name method. And let's just call this alien. Okay, so this is, again, perfectly compilable code. Now, what I wanted to show you is that this code compiles even if the lion and tiger have overrides. So if I override the name method, and let's just call this lion, I'm putting all these methods in line so that we can read them more easily. And again, if I override this in tiger as well, printing or returning tiger, again, this is perfectly compilable code. Because the class mutant extends lion with tiger, so it, in theory, tries to fetch in both implementations for name, but it overrides them. It overrides both of them, so the compiler doesn't care. It says, okay, I have a def name method, I'm fine. Whenever somebody calls my name method, I'm just going to return alien, okay? Now, the interesting problem is that this code compiles even if I remove this override. So this reduces to the classical diamond problem. We have our animal on top, we have lion and tiger as direct descendants of animal, and mutant as the somehow intersection between lion and tiger. So why don't we have a conflict here for the name method? Because extending lion with tiger apparently tries to resolve this conflict. We need to inherit both the name methods. So what does the compiler pick? Well, let's find out. We have a mutant, and let's just print out m.name. Let's see what this prints out. So as you see, the compiler doesn't complain, and it just prints tiger. Now, why is that? Well, that's because this is the same as mutant extends animal, which is the lion thing, with whatever line has overridden. So this is what the compiler thinks. With another thing which extends animal with whatever tiger has overridden. So whenever the compiler tries to parse this, it says, okay, mutant extends animal, so I'm going to fetch whatever animal has implemented. Then I'm going to override everything in here. So at this point, the name method returns lion. And then the compiler continues saying, okay, I'm looking at animal. Well, I've considered animal before, so I'm not going to look at it again. And then I'm going to consider this body, which overrides name yet again, and it returns tiger. So I'm going to use that. So that's why we see here the tiger string printed to the console, because the last override always gets picked. So I want you to keep this in mind whenever you have diamond inheritance. So I'm going to write this in all caps. Last override gets picked. That's how Scala resolves the diamond problem. Okay, so this is pretty cool, but also pretty scary. So be very careful when you have such inheritance models. Now, the item number 3 is the super problem, and a concept known as type linearization. We'll see what this means in a second. Now, what I'm going to ask you is that you remember what super does. So as a reminder, it accesses the member or method from a parent class or trait. Okay? So this is our current understanding of super, but in Scala, it has a wider significance. Let's write an example. Let's say we're modeling colors. Okay? So we have warm colors and cold colors. So let's say we have a trait called cold, and it has a method called print. Okay? And this just prints line cold. Super simple. Let's say we have a color class or trait called green, which extends cold. And this overrides print. See how the IDE suggested that I call super.print? Well, we are going to call print line green, and then I'm going to call super.print, which should print also cold. Okay? Awesome. Let's create a similar trait called blue that does basically the same thing. So blue extends cold and prints line blue, and then calls super.print. And then let's create a small class called red, which is its own league. And this also has a method called print, which prints line red. Okay, so we have red, green, and blue. And let's create a small class called white, which inherits from all of them. So extends red, which is a class, with green, with blue. And we override the def print method as I'm going to print white, okay? And then I'm going to call super.print. Now, I want you to take a few seconds to think about what the console will say if I declare a val color, which is a new white, and if I do color.print. So pause the video for a couple of seconds and think about what this thing should print to the console. Now, if you didn't even need to pause the video and said this would print white and red because the super.print just calls the print method from red, my friend, you would be so wrong. Let's run this and see what this thing actually does. So this prints white, and super.print prints blue, green, cold, but not even a trace of red. So what the heck is happening? So let's dig into this. We have a small type hierarchy starting with cold, and then we have two other colors, green and blue, descending from cold. We also have red, and all of those are converging into white. So in terms of the Scala compiler, we know that cold descends from any ref with some kind of other implementation. I've just noted this guy as the body or as the specific implementations that cold might add, all right? Then we have green as cold with whatever green has implemented or overridden, which is in fact any ref with the body of cold with the body of green. In the same fashion, blue is cold with whatever blue has implemented or overridden, and cold is then expanded further to any ref with whatever cold has implemented with whatever blue has implemented, okay? And red as well, any ref with whatever red has implemented. So white, being the descendant of all of them, is basically red with green with blue with the body of white, which the compiler then expands as any ref with the body of red, which is red, and then green and blue are expanded with their own expansions as any ref with cold with green and any ref with cold with blue, and then with the body of white, okay? Now, the compiler says, okay, I have a bunch of types and a bunch of bodies. So it takes all these elements in turn, and whatever it sees for the second time, it just jumps over it. So we have any ref with red, and then we see any ref with cold with green, but we saw any ref before, so we just jump over it. Again, in the third parenthesis, we have any ref with cold, which again, we saw before. So the compiler says, okay, white is then any ref with red, with cold with green, and then with blue, and then with white. Now, this is called a type linearization for white. Now, in the context of type linearization, the super keyword gets a whole new meaning. So in the context of this particular type linearization for white, if you call super, for example, from the body of white, this will take a look at the type immediately to the left in this type linearization. If you call super again, another element to the left. Super, another element to the left, and so on and so forth. So this is pretty tricky, okay? So here's our code example with the big type linearization on top so we can keep track of it, okay? So when we call white.print, we print, of course, white, and then we call super.print. But we now know what super does. Super looks at the type immediately to the left in white's type linearization. So in our case, it will look at the print method in trait blue, which will print blue, and then it calls super.print yet again, which will look at the type immediately to the left in white's type linearization, and that is in the green trait. So this will print green again, and it will call super.print again. So this will jump one element to the left yet again, so it will print cold. Okay, so as you see, this is very tricky in the context of complex type hierarchies. Alright, so I hope you've had a good warm-up, because Scala's type system is very powerful, but it takes good skill to properly handle it. But don't worry, that's why we're here. I'm Daniel, and I'm waiting for you in the next video.